Okay, we are on Le Chatelier's principle. Let's take a look at the warm-up. It says that consider the following equilibrium. We've got two SO2 reacting with O2 to create two SO3s. What is equal at equilibrium? Well, the forward and reverse reaction rates. Number two, what would happen to the forward rate if some O2 were removed from this equilibrium? Well, if you remove some O2, which is a reactant, you're going to decrease the forward reaction rate. Number three, explain why in terms of collision theory. Well, if you have less oxygen, you're going to have fewer collisions between oxygen and SO2, which are my two reactants. Number four, would the reaction still be at equilibrium at this point? No. So in 1888, Henry Le Chatelier wrote, every change of one of the factors of an equilibrium occasions a rearrangement of the system in such a direction that the factor in question experiences a change in a sense opposite to the original change. So to rephrase what he was saying, Le Chatelier's principle is that if we have an equilibrium system and we stress it out, maybe we stress it out by changing the concentration or changing the temperature or changing the volume, which would in turn change the pressure. Then we're going to shift either right or left to alleviate the stress that was caused so that we can somehow get back to equilibrium. Now, when we shift, we will only partially alleviate the stress. I can't emphasize the word partially enough, okay? So when I disrupt a system at equilibrium, we're going to shift in terms of the reactant and product concentrations. We're going to change one into the other to reduce that disruption to help us get back to equilibrium. And what Le Chatelier's principle helps us do is it helps us predict what's going to happen to an equilibrium's reactant and product concentrations when conditions change. So when we add reactant or product to an equilibrium system, we're going to shift to remove some of the added chemical, emphasis on some. And if we remove some reactant or product at equilibrium, then we will shift to replace some, emphasis on some, of the removed chemical. So an equilibrium system is a reacting system that's at or approaching equilibrium, and if we change the concentration of reactant or product, we're stressing it out. It's temporarily destroying the equilibrium. And it will respond by changing some of the reactants into products or vice versa. And if we are converting the reactants into products, that is known as a shift to the right. If we are converting product back into reactant, that is known as a shift to the left. Okay, so let's take a look at the next page at a sample problem. So here we have a system at equilibrium. It is hydrogen and iodine as reactants combining to make hydrogen iodide. It says some HI is added to the system below. So that means we are increasing the concentration of HI at equilibrium. So we are disrupting it. In which direction will the system shift to restore equilibrium? Anytime you add something, you're increasing the concentration of something. You shift away from it so that you can consume sum of what was added, okay? So if I am adding more product, what's going to happen is I'm going to shift to the left. And as I shift to the left, I'm going to consume some, emphasis on some, of the added HI to help me get back to equilibrium. And as I'm shifting left towards the reactants, that means I'm going to in turn increase the concentration of my reactant some with that shift. I won't remove all of the added HI. So overall, the increase of the concentration of HI will increase, but the concentration of H2 and HI will also increase, okay? If I had added more hydrogen or iodine initially, rather than adding HI, I would have shifted away from it, so I would have shifted to the right, and I would have increased the concentration of my product, consumed some of what was added for the reactant to help me get back to equilibrium, but overall the reactant concentration would have increased, okay? So let's take a look at another sample problem here. Here we have solid calcium hydroxide in equilibrium with a saturated solution of its ions. This is known as solubility equilibrium, and the rate of dissolving the solid equals the rate of recrystallizing it from its ions. We are removing some hydroxide by adding hydrochloric acid. Now, remember, if you're adding an acid will combine with a base, okay? So the acid that they're adding is hydrochloric acid. It will combine with the hydroxide ions. So it will consume the hydroxide ions and produce water while we're at it. Now, if the hydrogen ions are neutralizing from the acid some of the hydroxide ions to produce water. So that means the hydroxide ion concentration is going to decrease. In which direction will we shift? Well, I mentioned to you earlier, if we increase the concentration of something, we shift away from it because we want to consume some of it. Now, if I am decreasing in the concentration of something, I need to move in its direction to bring some of it back. So this is going to cause me to shift to the right to increase the concentration of my product. I need to replace some of this hydroxide, which I lost. I won't replace all of it, but I'll replace some of it. So the system is going to shift to the right. We shift towards the products to replace some, emphasis on some, of the removed hydroxide. Now, overall, since not all of the hydroxide is going to be replaced, the hydroxide ion concentration is decreasing. The calcium ion concentration is increasing because I'm shifting to the right. Let's go to the next page, take a look at the practice problems. Use the following system for questions 1 and 2. So we have iron combining with SCN to make FeSCN. What does Le Chatelier's principle say will occur if some FeNO3 is added to the system? FeNO3 dissociates into Fe plus 3 and NO3 minus 1 ions. So that means that you're really increasing the concentration of Fe plus 3. I told you that if you increase the concentration of something, you want to shift away from it because you need to consume some of it. So in this case, we're going to be shifting to the right, and we're going to consume some of this Fe plus 3. So Le Chatelier's principle says that system will restore equilibrium by removing some of the added Fe plus 3. So in which direction will I shift? To the right. When equilibrium is restored, how will the concentration of each substance compare to its concentration before the FeNO3 was added? If I'm shifting to the right, that means the concentration of FeSCN is going to increase, okay? And this SCN concentration, as I'm shifting right, is going to decrease because I'm consuming it. Since I had added Fe plus 3 ions, and I consumed some of it, but I didn't consume all of it, that means that overall the Fe plus 3 concentration increased because not everything was consumed. Let's take a look at number 2. What does Le Chatelier's principle say will occur if some sodium biphosphate is added to the system? The biphosphate ion reacts with Fe plus 3 to produce FeHPO4. So what that means is I'm going to be consuming Fe plus 3, which means that the concentration is going to be decreasing. So what does Le Chatelier's principle say will happen? Well, the system will restore equilibrium by replacing some of the removed Fe plus 3. Emphasis on some. Which direction will I shift? Well, since I was removing Fe plus 3 by adding that biphosphate, anytime you decrease the concentrations of something, shift in its direction to produce more of it. So that means we are shifting to the left. C. When equilibrium is restored, how will the concentration of each substance compare to its concentration before the sodium biphosphate was added? Okay, since I was removing Fe plus 3 by adding HPO4, that means the concentration came down. I restored some of what was lost. So overall, the Fe plus 3 concentration decreased because not all of it was replaced. And then as I was shifting to the left, I was producing more SCN. So that increased. But since I shifted to the left, I was consuming the product. So the product concentration decreased. Let's look at number 3. Look at the graph below. At T1, more H2 was suddenly added to the closed system as shown. Okay, so we're going to emphasize that H2 was suddenly added. So that's why you see this at T1. That's why you see the concentration of H2 suddenly increase, because it was suddenly added. Anytime you suddenly add something, you will see that line dramatically increasing that way, okay? At T2, equilibrium is reestablished. Okay, and here, this is when H2 concentration suddenly increased. Okay? Complete the plots to show how the system would respond. If this is my overall reaction and I increase the concentration of H2, anytime you increase the concentration of something, you shift away from it to consume some of it. So we have to shift to the right to consume some of the H2 that was lost. I will never consume, that was added. I will never consume all of it. So that means that over time, this concentration is going to be decreasing to a point where, I should probably draw that a little bit better, when you get to T2, it has to be leveled off, okay? That's T2. So I'm consuming some of it, but not all of it. Now, since I am shifting to the right to consume some of this, my I2 concentration, which is here, is going to have to come down. And then it's leveled off at T2. And my HI concentration, as I shift to the right, is going to increase. So this is going to come up. And it's leveled off at T2. Okay? Let's talk about the shift mechanism. The effects of stress on forward and reverse reaction rates. So a stress is any action that has a different effect on the forward reaction rate than it does on the reverse reaction rate. And disrupting equilibrium is going to occur, so that means that the forward and the reverse reaction rates won't be equal. If I look at this sample problem here, if I add some iron 3 chloride, which dissociates into iron 3 and chloride ions, that means you're increasing the concentration of Fe plus 3, and Fe plus 3 is a reactant. So what's going to happen? I need to consume some of it. So I shift away, I shift to the right. And if I shift to the right, I'm going to increase the forward reaction rate, which results in a net forward reaction, and that's known as my shift right. So in terms of the reaction rates, anytime you are adding something, you're increasing the concentration of something, you're going to notice a difference in that specific rate. So let me show you what this looks like here if we were to graph it, because this is really important to understand. So initially, this is my initial equilibrium, this E sub I. The forward rate equals the reverse rate. So this is the forward rate on top, and this is the reverse rate on the bottom, okay? This S stands for the stress that was caused. The stress that was caused here was we increased the concentration of Fe plus 3, which is a reactant. And that is why this forward rate increased so much. But you'll notice the reverse rate is the same because it's the same length as it was up above, okay? Now, the final equilibrium, which is E sub F, you will notice my forward and my reverse rates are now the same. And this forward rate came down a little bit and the reverse rate increased a little bit so that they would be the same, okay? If I were to graph this over here, this solid line is the forward rate and this dashed line is the reverse rate. So you'll see that there's a dramatic increase here in the forward rate when the concentration of Fe plus 3 was increasing, and then the forward rate came down as we consumed some of it, and then it leveled off at equilibrium, and then this reverse rate increased a little bit to meet it at the second or final equilibrium. Let's go to the next page. Let's take a look at another sample problem. Here it says that we want to explain in terms of the forward and reverse reaction rates how the system would react by removing some SO2. So we're going to decrease the concentration of SO2. Now, anytime you decrease something, we need to replace some of what was lost. We won't replace all of it, we'll just replace some of it. So removing some of the SO2 is going to actually decrease the forward reaction rate, and that's going to result in a net reverse reaction, which is why we shift to the left. So you'll see here, initially, at equilibrium, the forward and the reverse reaction rates are the same. Then, when I decrease the concentration of SO2, I decrease the forward reaction rate, which is here. And that was this stress that was caused by a decrease in SO2. You'll see that my reverse reaction rate is the same as it was initially at equilibrium. Then your final equilibrium, you'll notice that they both, the forward and the reverse, have come down overall in comparison to the initial. So when I add things, when I increase the concentration of things, my final rates, forward and reverse rates overall had increased, but when I take something away, my forward and my reverse rates have come down at my final equilibrium. Okay? Let's take a look here at the practice problems. Consider the following equilibrium system. Explain in terms of forward and reverse reaction rates how the equilibrium would respond to each of the following changes. First one, adding some NO. So if you increase the concentration of NO, which is a product, we need to consume some of it. So that means there's going to be an increase in the reverse rate, which is going to result in a net reverse reaction and that is why we shift to the left. What if I remove Cl2, which is a product? Well, when you remove something, you're going to decrease a rate. In this case, the reverse rate. And since I'm removing Cl2, I need to shift to the right to replace some of it. So this results in a net forward reaction, which is why I shift to the right. What happens when I remove some NaCl, which is a reactant? When you remove something, you decrease one of the rates. So we're going to be decreasing the forward rate, and this results in a net reverse reaction because I need to shift in the direction of NaCl to replace some of what was lost. So that's going to cause me to shift to the left. Number 2, show how the forward and reverse reaction rates respond to a sudden addition of NO to the system at T1. Use a solid line for the forward rate and a dotted line for the reverse rate. The system re-equilibrates at T2. Okay, so if we suddenly add NO, and NO is a product, anytime you suddenly add something, you're going to increase one of the reaction rates. So we're increasing the concentration of product. And since I'm increasing the concentration of product, I need to shift to the left to consume some of that added NO. So that means my reverse reaction rate is going to increase. So this dotted line, which is my reverse rate, is going to increase. Eventually at T2, it will come down and level off. Okay, so this is my reverse rate. Now, my forward rate has to come up to meet it. And that is my solid line. So it's going to come up to meet the reverse rate at T2, which is about here. So they should be the same at T2. Now, how would it look over here if I'm doing an arrow diagram to depict the same information? Well, initially, at equilibrium, the forward and the reverse rates are the same, but the reverse rate increased at the stress. So I'm going to make sure that that reverse rate is a longer arrow. And my forward rate stayed the same. Anytime you increase the concentration of a reactant or product, your final equilibrium arrows for the forward and the reverse rates are going to be a little bit larger than they were initially. So here we are showing them increasing, and they're both the same at the final equilibrium. Now let's talk about changing surface area and adding catalysts. In heterogeneous reactions, an increase in surface area increases the forward and reverse reaction rates equally, since both forward and reverse reactions occur at the same surface. So if I add more solid or I crush a solid that's present at equilibrium, there's going to be no effect on the equilibrium concentrations of the reactants and products in the solution. When the initial reactants have greater surface area, the system will reach equilibrium sooner. Similarly, if you add a catalyst, which is going to increase the forward and the reverse reaction rates equal, if I'm already at equilibrium, there will be no effect. But if I add a catalyst initially before I've hit equilibrium, I will reach equilibrium sooner. So, if initially I add reactants with greater surface area, or initially I add a catalyst, I will get to equilibrium faster. Okay, but it has to be initially. Let's take a look at the equilibrium position. Equilibrium position is referring to the concentrations of reactants and products present at equilibrium. It is generally represented by percent yield. This is a different percent yield than you're used to thinking of. You're used to thinking of percent yield as actual over theoretical times 100. And an equilibrium system with an increased percent yield is said to have an equilibrium position that is farther to the right. Let's talk about this equilibrium system here. So if I have HP, which is yellow, and I have P negative 1, which is blue. If I have a green solution, you know that yellow and blue make green. A green solution would mean that I have equal concentrations of HP and P negative, so I have a 50% yield. But if some yellow HP is added to a green equilibrium mixture, when you increase the concentration of HP, which is yellow, that's going to cause me to shift to the right to consume some of the HP that was added. So that means I should be turning slightly blue. So the equilibrium position is going to shift to the right to remove some of it. When equilibrium is restored, the solution would still be yellow because I wouldn't have consumed all of the HP that I had added. So the equilibrium position has shifted to the left. So when we say products are favored, that is sometimes using to describe an equilibrium system where I have greater than 50% yield at equilibrium. So more than half of the limiting reactant has been converted into my product. Now, without knowing which reactant is limiting, you really can't infer that any reactant or product has a higher or lower concentration than another solely from saying that the products are favored, okay? Let's take a look at the quick check on the next page. It says, state Le Chatelier's principle in your own words. Well, an equilibrium system subjected to stress will restore equilibrium by partially alleviating the stress. Number 2, according to Le Chatelier's principle, how will an equilibrium respond when a quantity of product is removed? Well, it will shift to replace some removed product. Emphasis on some. Number 3, how is a stress to an equilibrium system defined? That would be any action that has a different effect on the forward reaction rate than the reverse reaction rate. Number 4, how does adding a catalyst affect an equilibrium's forward and reverse reaction rates? Well, it increases them equally. Number 5, a chemist dissolves sodium bisulfite in a solution of nitrous acid. The following equilibrium is established with reactants being favored. True or false? We can infer from this that the concentration of HNO2 is greater than the concentration of H2SO3. That is true.